Evening, guys. My name is Sechanzi Elvis. Group one, and our title is Photo Voicing Accelerated Educational Content Generation using Large Vision Models. Basically, in Uganda, we have a large number of refugees. Basically, the curriculum on which these refugees are given education services basically relevant to their cultures. And with this, we've come up with a photo voicing accelerated educational content generator that will generate relevant educational content, basically that analyze within the competency-based curriculum that is currently in Uganda. So basically, with that, we aim at fulfilling the SDG 4 goals, that is quality education, equality, among others, so that refugees are able to get the quality education as other nationals. So one of my basically the PC is slow, but basically this is an overview. The photo voicing accelerated education content generator is centered on a single idea, basically leveraging generative AI to automatically create dynamic visual and narrated learning stories from a simple teacher's topic. Basically, a teacher say would get a given topic, maybe how to grow maize, and the education content generator will develop a story due to maybe images, in visual images in form of a story explaining how a person can grow maize from the first step to the last step. Basically, the reflection is the initial concept of this is a simple text to image pipeline that has evolved significantly into a sophisticated multi-component AI system, and this reflects a deep understanding of the real-world challenges. Basically, we've moved beyond generating single images to creating coherent visual sequences. That's like a form of a story, just explaining complex topics in form of a visual story that is easy to understand, and it is relevant to the competence-based curriculum. Basically, we recognized that the off-shelf AI models produce generic and often Western-centric imagery. Basically, we are overview. Basically, our education content generator is basically going to be producing our traditional content, basically away from the Western content. Basically, the existing models, basically some content generators, education content generators are available, but they basically based on the Western culture or the Western ways of doing things. So the one we are going to create, we are going to fine tune it so that it is able to use our traditionals. And this is going to be multilingual so that the different cultures of refugees in Uganda are able to acquire appropriately to their cultures. So the paper title one is Test Time Prompt Turning for Zero-Shot Generalization Language Models. Its abstract here, a pre-trained vision language model like LEAP have demonstrated remarkable zero-shot capabilities for image understanding and generation. This is a fault in CLIP, and basically this in educational context, particularly in resource settings like refugee settlements in Uganda, there is critical need to generate culturally relevant curriculum aligned visual content from simple text prompts. However, the effectiveness of the vision language models is highly dependent on carefully engineered text prompts, which are often suboptimal for specific localized education topics. And the existing methods improve performance, but they require downstream training data, which is scarce in these contexts and can reduce model generalization. Basically, the domain problem is I want to bridge the cultural and the contextual gap in the zero-shot education imagery. And this photo voicing system uses powerful large vision models to generate images from teacher prompts. That's a teacher can say maybe a topic like a child fetching water, so that a visual story in the form of visual images is created by the model. And this is very possible based on the competence-based curriculum topic that is basically invisible, and collecting large data set from Ugandan specific images to fine-tune the entire large vision model is computationally expensive and violates the offline first low resource principle of our system. Basically, the system we want to create should be capable of going on those low resource devices like simple tablets and simple smartphones here. And the pressing need is to adapt a general purpose vision language model to a specific culture and contextual needs of a teacher's prompt without requiring any additional basic training data or extensive computational resources. Here is a computational architecture diagram. Basically, we shall have that text encoder that handles the teacher's input. We have the image encoder, that is the narrative for narrative structuring. The TPT loop, this is a refined prompt that enters the loop, and the output, basically the loop concludes with an optimized detailed prompt that is contextually aware, and this prompt is then passed to the final image generator to produce high quality culturally relevant image for learning the model, as you see from our architecture. The text encoder, then to the image encoder, and then we have the loop, that is the confidence selection, then to the back propagation. So the second paper title is Sequential Modeling that enables scalable learning for large vision models. And here the abstract here is the emergence of large vision models trained sequentially on vast, diverse visual data without any linguistic input presents a paradigm shift for generating educational content in linguistically diverse resource settings. And this work explores the integration of sequential large vision model architecture into our photo voicing pipeline for generating curriculum-aligned visual narratives inspired by sequential modeling. This enables scalable learning for large vision models, and we propose representing all visual data, including raw images, instructional graphics, annotated frames, among others. So the domain problem is this is the data scarcity and linguistic bottleneck in vision-centric learning, and the core limitation deploying artificial intelligence for education contexts like in Ugandan refugee settlement is the heavy reliance on language. Basically, we rely too much on the Western language, and this vision language models require high quality, well-paired image to text data, which is scarce for local contexts. Basically, if we want to produce ours locally. And furthermore, generating a sequence of images requires maintaining visual consistency and narrative flow, a task that is challenging for models that treat each image generation as independent. There is a need for a unified vision-only foundation model that understands and generates visual narratives based on patterns learned from billions of visual sequences. So, as we go to the next page, basically, it is the computational architecture. And as you see, we have the VQ-GAN decoder and the VQ-GAN decoder, and we have the tokens and the auto-regressive vision model. Then down we have the VQ-GAN encoder. This is for the visual sequence, and the VQ-GAN encoder also on the left. So this is the architecture of the large vision model, and we first convert the individual images from a visual sentence into discrete tokens using the VQ-GAN encoder. And basically, stage one, we have foundational model training, that is pre-training. Then we have visual prompting and inference. That is where the teacher will input a topic, and then the visual sentence encoder will work on the topic to produce visual images relevant to the topic and that are easy to understand. So this is the paper, the third paper, and the title is Object Detection with Vision Language Models. So basically, abstract, this proposes the integration of multimodal large vision language models for advanced object detection and localization to enrich the visual storytelling capability of, to enrich the visual storytelling capability of the photo voicing educational content generator. The current pipeline generates coherent image sequences and lacks fine-grained control over specific objectives and their contextual relationships with the scene. Leveraging insights from the in-depth review on the large vision language models, we incorporate a dedicated visual grounding module that utilizes the shared language vision understanding of large vision models. And this module allows educators to specify not just the overall scene, but also key educational objects. And the large vision language model based detector can generate images where these objects are accurately localized, contextually interrelated, and culturally recognizable. And the problem here is the lack of fine-grained pedagogical control in generated imagery. And this is a shortfall in generative models for education due to the inability to reliably control the presence, attributes, and spatial relationships of specific objects within the generated scene. So the traditional object detectors like YOLO are not suitable for this generative task, and they are discriminative models that require extensive datasets for every new object and lack the ability to create images. So the pressing need here for a generative model is the descriptive precision, a system that can understand complex language-based requests for a scene and ensure that specific objects are not only present, but also correctly localized and contextually situated within the generated image. So here is the architecture of the content generator. So as you see, the architecture introduces a dedicated model that uses a large vision language deep understanding of language vision to guide the image generator with precise spatial and contextual controls. We have the enhanced prompt, as you see, the text prompt. We have the visual fine-tuning as a step, then zero shot imaging. Basically, this is an illustration of a 3D. The paper title 4, this is the video MME, the first ever comprehensive evaluation benchmark multimodal large language models in video analysis. And here This evolution of the multimodal language models has predominantly focused on static imagery, leaving significant gap in the ability to understand and reason about sequential dynamic visual data. And this work proposes to leverage the comprehensive evaluation framework of video MME to integrate advanced video understanding capabilities into our photo voicing educational content generation system, recognizing many competence-based topics are inherently procedural. We aim to evolve our system from generating static image sequences to producing or understanding cohesive short-form educational videos. Here, the domain problem, this is due to the static nature of the current visual narratives and the lack of residual assessment. And this current photo voicing pipeline generates static image sequences. While this is a significant improvement over text, it fails to capture dynamic procedural nature of many competencies outlined in the competence-based curriculum. So skills like demonstrating proper hand washing technique, navigating safe download are acquired. So we have the computational architecture. Basically, the architecture uses a video capable large language model as a central reasoning engine for dynamic content, and the first step is model selection via the video MME. And here, before integration, various AMLLMs like Gemini 1.5 and others are evaluated using video MM benchmark. And the second stage here, we have dynamic content creation and decomposition, where a teacher will input a text and will require a visual-based video showing or narrating according to the topic. And stage 3 is a multimodal procedural assessment that has multimodal fusion and assessment and automated feedback report. So here is a paper 5 title. Here it is learning to prompt for vision language models. And abstract is vision language models like LEAP offer transformative potential for zero-shot educational content generation, and yet their effectiveness is critically dependent on handcrafted prompts and a process that is both time-consuming and culturally brittle. And this work integrates context optimization, a prompt learning technique, into our photo voicing pipeline to automate and specialize the prompt engineering process for a Ugandan competency-based curriculum. And instead of relying on static generic prompts, it introduces a set of learnable context vectors that are continuously optimized using a small dataset of local culturally relevant images and their descriptions. And this allows the system to automatically discover optimal prompt contexts, like a vibrant Ugandan illustration of an educational diagram showing a local example of significantly enhancing the cultural relevance and pedagogical clarity of generated imagery without modifying the core VLMs or vision language model weights. And this problem statement here, this is due to the inefficiency and the cultural insensitivity of the manual prompt engineering, and the deployment of large vision language models in specific culturally distinct domains like Uganda, refugee education is hampered by the prompt engineering bottleneck. And manually crafting the perfect text prompt for each competence-based topic. Here is the computational architecture. Here we have the text encoder that works with the educator's text input, and we have the image encoder for producing, it works with the visual imaging. So the first step will be offline core model training. Here we shall have a small data set and base prompt template, and the training loop. And the stage 2 is inference and content generation, where a teacher will input a text and prompts the engine, then image generation starts, and the image produced will be relevant to the teacher's topic. And the sixth paper title is the intern VLM, scaling up vision foundation models and aligning for generic visual linguistic tasks. And the abstract, and here this paper presents an intelligent AI-powered photo voicing system designed to address the critical shortage of engaging and culturally relevant education materials in refugee settlements in Uganda. And the system leverages state-of-the-art large vision language models to automatically transform topics from Uganda's competency-based curricula into narrated visual sequences. Here, a teacher can input a text like how to grow maize, and the platform will generate a coherent series of culturally contextual images synchronized with culture, natural, and multilingual text-to-speech. Multilingual text. The system creates a speaking photo experience, and this approach is specifically optimized for offline low-powered devices, making it a scalable solution to accelerate comprehension and bridge literacy gaps and faster inclusive quality education, like that is SDG4 in low resource and multilingual environment. And the technical problem here is due to lack of tools that allow non-technical educators to rapidly generate high quality competence-based curriculum aligned and visually rich digital learning content. And the core technical challenge is to create an automated pipeline that generates culturally relevant visuals. Basically, here is the computational visual architecture diagram. Here, first is input and curriculum mapping, and here the educator will input a competence-based topic where the system uses a topic-driven narrative, TDNO, to potentially powered by a large language model like GPT-4 to decompose the topic into structured narrative aligned learning sequences. For example, if a teacher says how to grow maize, the topic will be decomposed into steps in which maize is grown. Those are text-based. Then images will be generated according to those steps that are broken down. So the visual asset generation, basically the paper title 7 is Flamingo, a visual language model for few short learning. And the abstract here is the system leverages advanced visual language models capable of few short learning to rapidly adapt to new topics within the competency-based curriculum. Here, a teacher can prompt a topic like the water cycle and provide just a few examples of desired visual sequences, and the system then generalizes to produce a coherent series of culturally contextual images synchronized with multilingual narration. And with multilingual, we mean the system will be taught or trained on a number of languages according to the culture, so that different languages of variant cultures are made. And this approach optimized for offline low-power devices and offers scalable and rapidly adaptable solution to bridge the literacy gap. And the computational problem, basically, it's generating the content to its efficiently and contextually based on a few examples. And this involves overcoming data scarcity for niche topics, manually collecting a large data set for every possible competence-based curriculum topic, and this is basically infeasible or not feasible. And the system must learn new visual concepts for every few annotated examples, which is a problem. And so sequential multimodal understanding, the system must understand and generate relevant visual content. Basically, here is the computational visual architecture with Flamingo, and here we have the passive resampler, and that is the vision encoder. So The architecture integrates Flamingo's component to create dynamic few-shot learning pipeline. And a few-shot prompting and input, the educator provides a target topic. So we have multimodal sequence processing, which is Flamingo's core. Also, we have the vision encoder, which is a pre-trained vision network that processes all input images from a few-shot example and new topic prompt. Basically, you have perceivable sampler, the gated cross attention dock, among others. The eighth paper is conditional prompt learning for vision language models. And here the abstract, here the system leverages large vision language models enhanced with conditional prompt learning to achieve precise cultural and pedagogical alignment with competence-based curriculum. Instead of relying on manual prompt engineering or full model fine-tuning, our approach learns dynamic image conditioned prompts that guide the model to generate highly relevant visuals from simpler teacher inputs. That's for topics. Basically, a topic can be maybe a mathematical topic, like adding two numbers or multiplying two numbers. So it will be broken down into steps and it will show visual images of how this process is done. And the technical problem here is to efficiently adapt a massive pre-trained vision language model to a very specific domain, Ugandan competence-based curriculum, without catastrophic forgetting, overfitting training classes or computational infeasibility. So the static prompt and also the static prompt problem using a fixed handcrafted prompt. Computational visual architecture. Here, the key innovation is the additional prompt learning module that sits between the teacher's input and the large generative models. That is the text encoder and the image encoder. So the input topic encodings here, the encoder inputs a competence-based curriculum topic, and this topic is converted into a class token. As you see, the context token V1, V2 to VM. Then we have the conditional prompt generation. Then the topic is fed into the prompt template, and in standard COOP, the context words seeking a photo of are replaced with the set of static learnable vectors that are optimized during training. And our approach, this is the 9th paper, BRIP2, bootstrapping language image pre-training with the frozen image encoders and large language models. And here the abstract is that the paper presents an intelligent, artificial intelligence-powered photo voicing system designed to generate narrated visual stories for refugee education in Uganda, and the system leverages a highly relevant, highly efficient vision language architecture inspired by BRIP2 to bootstrap powerful pre-trained models without cost of end-to-end training, and by using lightweight querying transformer to bridge a frozen image encoder and a frozen large language model. And the system basically understands educational topics and generates coherent narrative scripts. And this will allow the teacher to input a topic like, basically, if it talks about soil erosion, this topic will be subdivided into different processes in which soil erosion occurs, and then visual images are created according to the different steps in the topic, formulating a visual story. And here the computational problem or technical challenge is to bridge the powerful but separate fields of vision and language without the prohibitive cost of training massive model from scratch. So no need for training model from scratch. We use the currently available models. And this solves the modularity gap, it improves training efficiency and inference efficiency. So this is the computational visual architecture, and here we have the image encoder, the input image, then the image to text. We have the Q-format where we have image to text mapping, the image to text contrastive learning, and the image grounded text generation. So the Q-format the input and visual processing. The educator inputs a topic and the system can optionally use an image or a sketch as a visual prompting. This visual input is processed by a frozen pre-trained image encoder. That's like Intern Vit or ClipVit. So we have the conditional asset generation. Then the 10th paper title is a survey of state-of-the-art large vision language models, alignment, benchmark, evaluations, and challenges. The abstract here, informed by comprehensive surveys of the field. This work navigates key vision language challenges such as visual hallucination, cultural misalignment, and safety to build a robust solution for generating narrated visual stories from the competence-based curriculum. And we implement a hybrid pipeline that leverages efficient state-of-the-art architectures like BRIP2 and Flamingo, and advanced alignment techniques like conditional prompt learning to ensure generated content is pedagogically accurate, culturally relevant, and contextually grounded. And the system rigorously is designed to work on offline low-power deployment devices, making it scalable, evidence-based tool to accelerate comprehension, bridge literacy gaps, and advance inclusivity. The computational problem, this underscores the vision language models that are transformative for enabling machines to perceive and reason about the world, which directly validates the core premise of the project. Using artificial intelligence to help learners perceive and reason about educational concepts, and it is positioned at the forefront of applying this transformative technology to critical humanitarian needs. The use of control net adapters basically will help. Then the architecture, we have the text encoder, we have the vision encoder, the text encoder for text description, we have the text encoder. Then the image, we have the vision encoder. Then from the text encoder, you have text embedding. It will pass through to contrastive learning, then to the decoder and pre-training objectives, then to the vision language model. So contrastive pre-trained models like CLIP are used for foundational view understanding and zero-shot cultural alignment. Then interface models such as BRIP2 are used as efficient bridges to extract visual information and connect large language models. We have generative models such as Stable Diffusion and ControlNet. These are used for the final visual asset synthesis conditioned on the output of the interface models. Then we have the prompt-based alignment. This method is for efficient steering the frozen components of the above models. Use this. So we have the unified concept of all the 10 reviewed papers, and here the abstract, a unified pipeline that synergistically integrates 10 state-of-the-art advancements in large vision and vision language models to address the multifaceted challenge of creating dynamic curriculum-aligned learning materials for low-resource multilingual settings like Ugandan refugee settlements. This moves beyond static image generation to produce cohesive short-term educational videos with embedded assessment by combining test-time prompt tuning for cultural specificity, a sequential large vision model for visual narrative coherence, and large vision language model-based visual grounding model for fine-grained control, and video multilingual language model for procedural understanding. The system ensures pedagogical precision and efficiency is maintained through BRIP2 frozen model bootstrapping, Flamingo's few-shot learning, and conditional prompt learning. The domain computation problem here, the challenge is multimodal or multi-constraint educational content generation problem where no single existing model can simultaneously interpret a teacher's simple prompt and decompose it into a culturally aware procedurally correct narrative, and this generates a sequence of visually consistent dynamic assets in form of images or video clips where specific objects are accurately localized. Attempting to solve this with a patchwork of disconnected systems and leads to incoherent outputs, computational bloat, and maintenance nightmares. And in fact, purpose-built architecture is required to orchestrate these capabilities seamlessly. And this is the computational architecture. And basically, we have here where a teacher types a simple topic, how to wash hands. So the topic will basically be broken down into different steps, simpler steps, and those visual images will be created as per a step. Here we have a smarter planner. This is the first artificial intelligence step that breaks the topic down into logical step-by-step storyboard. Like the steps of washing hands, step one, okay, for example, turn on a tap. Step two, apply soap like that. And visual images will be created. So that's all.